Hello everyone, welcome to the channel of Algocamp. So in this particular series, we are going to start talking about a few interesting concepts around data structures and algorithms. These videos are going to be power packed with in-depth explanations, problem solving around some very important aspects of data structures and algorithms. DSA is one of the most important topics when you see software engineering interviews for both internships roles and full-time roles. And I see that a lot of people actually struggle with that. So in this particular video series, what I have tried is I have tried to make sure that I try to solve the problems and try to explain the corresponding concepts with a more intuition building kind of like a scene. And we will be doing a lot of pattern based problem solving so that you can actually see what kind of problems can be solved with a specific type of algorithmic pattern. In this particular start of the series, we are going to actually start with searching algorithms. I believe searching algorithms are one of the most important algorithms if you want to actually excel in DSA, and a lot of advanced concepts in DSA do rely on searching algorithms. So without any further ado, let's just start this particular video, but I would highly encourage you to do subscribe to the channel if you have not yet subscribed, because we are going to put some really awesome content coming up ahead, and all of these videos are going to be really helpful for you for preparing for your next software engineering interviews. So let's just start. Also, if you are somebody who is actually willing to prepare for software engineering interviews and want a more structured curriculum around high-level design, low-level design, other aspects of interview preparation around system design, or you are more interested in around learning back-end development concepts with Node.js, Spring Boot and whatnot, then do check out the website of algocamp.io. Here we have tons and tons of live courses where we talk about some really interesting concepts around software engineering. So do check out the website and start preparing for your software engineering career, because all of the concepts that we are going to talk about are one of the most important ones to become a better engineer and also to actually crack all the software engineering interviews. So let's come back to the video. So this is a new problem statement in front of you. The problem says that given a sorted array of length n having integers in the range 0 to n minus 2, every element is present once, but only one element is present twice. You have to find the repeating element. So you can see this array is of what length? 3, 6, 7, 8, right? Array length is 8. You can see the elements are in the range 0 to 8 minus 2. It's a sorted array. Every element is present once, only one element is present twice. You have to find this element, right? So the answer will be 2 for this test case, right? And you have to find this in something better than order of n. Do something better than order of n, right? So this is a new problem in hand. Let's see, let's take a pause here and try to think that how you can solve this problem in something which is in a time frame which is less than order of n. So what will be the brute force solution of this problem? If you see, then in brute force we can just apply a basic linear search kind of a thing. Why? Because what we can do, we can iterate over every index, right? We can start from the first index and start iterating over every index. If the ith index, let's say this is I, if the ith index value is equal to the I minus 1th index, then this is the culprit element. You can see 1 is not equal to 0, 2 is not equal to 1, but this 2 is equal to its previous index. So what we can do is just check if the ith index is equal to the I minus 1th index for all I that belongs to the range 1 to n minus 1. Okay, right? This can be a simple linear search based approach. The time complexity of this approach is going to be order of n, but we technically need to do something better than order of n. So let's see. If we want to do something better than order of n, right, we can observe a pattern here. What pattern we observe is that if you write the indexes of the element, if you write the indexes of the element, then what you will realize is that after the element or after the repeating element, there is a change in pattern that occurs, right? Previously, prior to the repeating element, the index value is equal to the index only. The value at the index is equal to index, value at the index is equal to index. But post the repetition element, this is not the case. Post the repeated element, the value of the index is equal to index minus 1. Value of the index is equal to index minus 1, right? So we have kind of like an observation based on which we have two different parts of the array that possess two different properties. So the intuition says that if you can divide your whole array into two parts and then do some manipulation, how about you try with binary search? How about you try with binary search? What you can do with binary search? Okay. So let's say we set up our search space as low and high as the 0th element of the array and the last element of the array. And then I try to divide my array into two equal halves. So 7 plus 0 by 2 is 2. Sorry, 3. 7 plus 0 by 2 is 3. So this is our mid. Now, here you can see the value of mid, ARR of mid is equals to mid minus 1. Can I say that? That means at the current index, we already have been affected by the repeating element, right? Either this is the repeating element or we are at some element which is already affected by the repeated element. For example, if let's say 1 was the repeated element, then I can say that here also you can see ARR of mid is equals to mid minus 1. So either we are already affected by the repeating element, or this element is itself the repeating element, right? Two cases can be there. In case of 2 comma 2, this element is itself the repeating element. So I can write that if we hit a mid that satisfies the given condition, then we can say either mid is the answer or mid is to the right of answer, or mid is to the right of answer. For example, if you have a 1 here, then mid is to the right of answer. If there is a 2, then mid is answer itself. Now, how can you check whether mid is answer itself? The moment you realize that ARR at mid is equals to mid minus 1, then you can just check if ARR of mid is equals to ARR of mid minus 1. That is, whether the current index value is equal to the previous index or not. If these two indexes are same, then this is the culprit element, right? So what I can say is that if ARR of mid, let me write it properly. If ARR of mid is equals to mid minus 1, then we are going to check that if ARR of mid is equals to ARR of mid minus 1, right? If this is the case, then return mid because mid is the only culprit element. But let's say this is not the case. This is not the case and we have a 1 here, right? So mid is not equal to mid minus 1. So if mid is the value at the middle index is not equal to the mid minus 1th index, we can say that we are in the region of the affected part where the culprit or the duplicate element has affected this ratio. What ratio? Or I would say what relation? That prior to the repeating element, the index was equal to the value at the index. But now you can see after this is not the case. So I can say that if I am at a value such that ARR at mid is equals to mid minus 1, everything to right of myself, all of these are affected values, right? All of these are affected values. So if I am not the duplicate element, these elements are also of course not the duplicate elements. The duplicate lies on the left side. There is no point of searching the right side. There is no point of searching the right side. The duplicate is going to be on the left side. Can I say that? So the two halves are divided based on the fact that the whole right half is affected by the duplicate element, but the whole left half may or may not be affected by the duplicate. For example, 0 and 1 are not affected by the duplicate, and technically this is the duplicate. So this is the property based on which we will say that we should discard the right half. So how do you discard the right half? You do high is equals to mid minus 1, right? Otherwise, let's say you do something like this. Okay, let's say we have a situation like this where ARR at mid is not equal to mid minus 1, but instead it is equal to mid. We can say else if ARR at mid is equals to mid, and I can say this is the only extra case that can happen. So no point of keeping else if. I can just write else and things will be same, right? I'll just say else. Now, if this is the case, then can I say that if the current index is having the same value as of index, then everything to the left of it is also going to be correct. All of the elements to the left of the middle element are going to satisfy the fact that the value at the value at the corresponding index is equal to the corresponding index, right? So you can see at the 0th index we have 0, at the first index 1, second index 2, third index 3. So if we hit a mid which is following the fact that the value at index is equal to the index only, then everything to the left of it is also correct. No one has been impacted on the left side, but we can't say for sure on the right side. On right side maybe some element might be impacted. For example, if this was 4 5 5 6, then 4 is not impacted, but 5 is not impacted. This 5 is the culprit element and 6 is impacted. So we can't say for sure about the right side, but we are definitely sure that on the left side we are never going to find our answer. So we are going to eliminate the whole left side, and if we eliminate the whole left side, you can say low is equals to mid plus 1. That's it. And we are going to repeat this process. We are going to repeat this process inside a while loop again and again, calculating the mids till the time low and high are still having some valid search space, right? So we can say while low is less than or equal to high, okay, and that's it. You can see the time complexity of this loop is going to be what? Order of log n, and the space complexity of this loop is going to be order of 1. So we have solved this question, which initially looks very overwhelming, with the fact that maybe we have to do linear search, how we can do less than order of n and so on. But due to the fact that the array is sorted, we were able to make sure that we are somehow able to divide our search space into two parts and then try to apply binary search. So this is also a very interesting question on binary search, right? I hope you guys will be able to implement it, but I believe the overall logic of the problem is clear to everyone. So this problem is coming from LeetCode, more than 13,000 upvotes. Problem number 41, marked as hard. I also believe it's a hard problem. First missing positive number. So given an unsorted integer array nums, you have to return the smallest missing positive number. Now there is no pattern, nothing in the array. It's just that it's an unsorted array. You have to just return whatever is the smallest missing positive number. You must implement an algorithm that runs in order of n time. It says it and uses constant extra space, right? So technically they want us to not use any extra space, right? But first of all, let's just try to think about the problem with extra space. At least we will be able to think about the problem in that terms, and then let's say we will try to figure it out. Okay. They have nowhere mentioned that we cannot modify the array. They have nowhere mentioned that we cannot modify the array. That means we can modify the array. So if you remember the modification approach that we did in the last problem, maybe that can help here. But let's see for the time being. For example, there is 1, 2, 0, then the element missing is 3. If the elements are 3, 4, minus 1, 1, then the element missing is 2. If there is 7, 8, 9, 11, 12, then the element missing is 1. Okay, cool. Now what can be done here? What can be done here? If you see, like the basic, let me close this. One basic approach that is kind of like a optimized Brute force is, first of all, what will be the brute force? The brute force will be start iterating from 1 to n. I is equals to 1, I less than n, I plus plus. And then in your array, iterate over the whole array and check whether I exists or not. Right. So you can check for j equals to 0, j less than a dot length, j plus plus. You will check if a of j is equals to y. Right. You're going to check whether this element exists or not. If this element doesn't exist in the whole array, then this element is the first missing element. But this approach is going to take order of n square. Order of n square. That's too much. If we want to optimize, then we can say that how about if we calculate the minimum element and the maximum element? Like calculating the minimum and maximum from the array is very trivial, right? In order of n time, you can calculate minimum and maximum. And then what you can do, you can prepare a hash map, or you can say you can prepare a mapping. Okay. This mapping, you can, let's say, prepare a frequency map. Okay. Then you can iterate from the minimum element to the maximum element. You can iterate from the minimum element to the maximum element, right? And then inside this range, let's say we say for I is equals to minimum, I less than equal to maximum, I plus plus. If the value I is negative, we don't care about it, right? If I is less than 0, we continue. Less than equal to 0, we continue, right? We don't care about negative elements and 0. The moment we reach the positive range, we will check whether this element I exists in the mapping or not. If this element exists in the mapping, then no problem. But if the element doesn't exist in the mapping, and the first element that doesn't exist in the mapping will be my answer, the time complexity will be order of max minus min. Space complexity will be order of n. Now this will give you time limit exceeded. Why? Because the maximum and the minimum element can be of the range 10 raised per 9. See, 2 raised per 31 is approximately 10 raised per 9. So this solution will give you TLE. But you can optimize this solution. You can say that I don't need to go from minimum to maximum. I am just concerned about positive elements, right? So how about I go from 1 to n? And then for every value of I can just check whether the value exists inside the frequency map or not. In this way, I can reduce the time complexity to order of n and space complexity also to order of n. Right. Now you might be thinking that how will you detect n? Here you can see that in the worst case, if every element is positive, like if all of the elements are correctly present, right? If all of the elements are correctly present, then you can say that everything will be there from 0 to n, or you can say from 1 to n, everything will be present, right? For example, if you have an array like this, 1, 2, 3, then the first missing number is 4. Can I say that? So we know that whatever is going to be my answer, right? That answer is going to be in the range 1 to length of the array plus 1. Can I say that? Whatever is my answer is going to be in the range 1 to length of the array plus 1. For example, if you see this 7, 1, 3, 8, 9, 10, 11. Now what is the length of the array? 3, 3, 6, 7. 7 is the length of the array. I am saying my answer will always lie in the range 1 to 8. See, 2 is missing. 2 is missing, right? So 2 is my answer. And why I am saying that answer will also always lie in the range 1 to 8? Because in the worst case, when all of the elements are positive and are present of the given range, like 1, 2, 3, 4, 5, 6, 7, if we tightly pack this array, then the only element that is not present and is positive, which is smallest, is the n plus 1th element, right? Otherwise, if any one of these are missing, even if 4 is missing, or even if 7 is missing, then my answer is definitely going to be less than 8. So I can say that my answer is going to be in the range 1 to 8. or you can say 1 to n plus 1. So I can just iterate from 1 to technically n plus 1 and check in the mapping, right? But the problem says that you cannot even use extra space. You have to use constant extra space. But the problem nowhere says that you cannot modify the array. So this time our modification algorithm will work. That is, let's take an example. 3, 4, minus 1, 1. For the time being, if I consider it 1 based, if I consider this array 1 based, what I'm going to say is that if you see a negative element, just avoid it, right? If you see a negative element, just avoid it for the time being, okay? And what you can do, you can start iterating from I is equals to 1 to I less than or equal to n plus 1, I plus plus, okay? Let's try to do this. Now what I'm going to say is that or let's we don't even take this loop. Let's not even take this loop first. Now let's say that we have 3 here. How can we mark the presence of 3? I can go to the index 3 and make it something which might technically not be present. We will think about that problem, that what you can update it with, no worries. But for the time being, we can say that we can mark the attendance, or I would say mark the presence of 3 by modifying this value. We can mark the presence of 4 by modifying this value. We can mark the presence of 1 by modifying this value. The only presence we won't be able to mark is of 2, right? So this will be the only element which will not be marked. Now we have to figure out how can we mark these these numbers. Now let's just think about it. If I make all of the elements negative, now we have some negative elements. I say we don't care about it. We will ignore it. Why? Because let's say 3 is going to make it negative. It is already negative. If it is already negative, no problem, right? 4 is going to make this negative. I'll make it negative. 1 was going to make this negative. I'll make it negative, right? So if any element is already negative, leave it as it is. If the element is positive, mark it negative. Because eventually if this was positive, then also we were going to make it negative. Somebody has already made it negative for us, okay? And existence of this element doesn't hamper, because I don't want to care about the negative elements. Now the first index where a positive element is present, that index my answer, right? Because we want to get the smallest missing positive number, right? We want to get the smallest missing positive number. This is the essence of the problem. Let's take one more example. Like, okay, let's say all positive numbers. Now, if you go, you mark this negative, you mark this negative, you mark this negative, right? And for marking negative, of course, you are going to take absolute value, right? For marking negative, you will take absolute value, right? So now using this one, you can mark this as negative and so on, right? The first positive number like 2 will mark this as negative, okay? And 5 is there. Nobody is going to mark this as negative. Right? Because 5 will mark this negative. This is the first index which will be positive, which will not be marked negative. And this is our missing element. Can I say that? Now the only corner case that we have to handle is that once we are making them negative, let's say we made this 3 negative, okay? So we go to this index and we made it negative. We go to this index, we make it negative. Now we came at this 3. How do we know if it was a negative element or we have made this a negative element? Because if we made this a negative element, then technically we need to consider its absolute value and go to that index and make it negative. But if it was already a negative element, If it was already a negative element, then I don't care about this value, right? See, this was already a negative element. I don't care about its absolute value. So what we can do is, inside your array, before you start processing these negative elements, you can replace all of the negative elements, let's say by 0. Replace all of them by zeros. Why? Because you are considering one based indexing, right? You are considering one based indexing. Now see what happens. You try to mark this as negative, this is already 0, doesn't matter. You try to mark this as negative, this is 0, 0th index doesn't exist. You try to mark mod of 1, this as negative. The first positive value, which is non-zero and non-negative, is index 2. Let's bring the same situation here, right? If let's say it was already -1, then if 3 will try to make it -1, how will we distinguish that whether its contribution we have to take or not, right? So what we are going to do, we are going to replace it with 0. Now 3 will try to make it negative, it is already 0, doesn't matter. 4 will try to make this as negative. Now this 0 can never make anyone negative, right? So no problem. Now this -1 exists because the original value was +1. Somebody made it negative. Because if it was originally negative, then we would have replaced it by 0, right? So we'll make it positive and then update -3. Nobody updated this, so we'll go to the first index. It is already negative. This is already negative, we'll leave it. Fifth index is going to make this negative. This is already negative. We'll make 4 as negative and already negative. At last, the first index, which is having a non-zero positive value, non-negative, non-zero positive value, is index 6. So you can say that nobody updated 6. So 6 is the missing element from our given array. So using this approach, we can technically solve this problem. I hope this approach is clear, and this is going to take order of 1 space, order of n time. As simple as that. So based on of our last problem, or the one of the approach of the last problem, where we were updating the I would say values of a particular array, using that approach, this problem is technically solvable. So this is a new question coming from lead code problem number 74, search a 2D matrix, right? What you have been given is that you have a m cross n integer matrix with two properties. Each row is sorted in non-decreasing order, right? You can see every row is sorted in non-decreasing order, that means ascending order. So every row is sorted. The first integer of each row is greater than the last integer of the previous row. So for every row, if you will check the first integer of any row, it's always going to be greater than the last integer of the previous row, right? Given a target value, return true if target is present in the matrix, or false otherwise. Okay, or false otherwise. So now let's say if you keep the matrix like this, okay, let's say if you have the given matrix looking something like this, okay, 1 3 5 7 1 3 5 7 10 11 16 20, I'm just writing it down, 23 30 34 60, okay. And what's the target? Target value is, let's say, 3. Okay, cool. So let's say this is the given matrix. This is the given matrix. This is the given 2D array. Okay. And let's say your target value is equals to 3. Now you can see that every row is sorted in ascending order, and last value of every row is less than the first value of the next row. So what can be a brute force solution for this problem? What can be a brute force solution for this problem? The brute force solution of this problem can be to traverse and read the whole matrix. Can I say that? We can one by one go to each and every single value of the matrix and see if this value is equal to the target, if this value is equal to the target, if this value is equal to the target or not. Right? In this way, what will be the time complexity? Time complexity will be mn, considering there are m rows and n columns. Okay. Now, how can we optimize? We can optimize by looking one simple fact that every single row is sorted. If every single row is sorted, then a simple optimization, I would say optimization 1, a simple optimization can be the fact that you can apply binary search on each single row. Let's say you apply binary search on this row, you apply binary search on this row, you apply binary search on this row. Why? Because this row is arranged in ascending order, this row is arranged in ascending order. And we know that if there is an array arranged in ascending order and we want to find a particular element, we can very easily do that with binary search. So another interesting approach can be to apply binary search on every single row. What will be the time complexity if you will apply binary search on every single row? How many rows are there? M. On each row you will apply binary search, which is of complexity log n. So the time complexity comes as m log n, right? You have to go to each single row. There are total m rows and you apply binary search on each single row. So that is log n, log n, log n. Can I say that? Right. Okay. Now, can we optimize further? Can we optimize further? Now, an interesting part is that because every row is sorted and the last element of the every row is less than the next element of the first row, oh sorry, less than the first element of the next row, you can actually visualize it like a 1D array only. Like I could have visualized it like 1, 3, 5, 7, 10, 11, 16, 20, 23, and so on. Can I say we can visualize this like a single 1D array only, right? If you visualize it like a single 1D array, this single 1D array is also sorted in ascending order. See 1, 3, 5, 7. Then 7 is less than 10, 10, 11, 16, 20. Then 20 is less than 23 and so on. So this single 1D array is also arranged in ascending order. So one approach can be that you store all of the elements of this 2D matrix in a m cross length array. So what you can do is you can take extra space. You can take extra space and store all the elements of the matrix in a m cross n length 2D array. M cross n length 2D array, right? And apply binary search. Can I say that? So in this way, what is going to happen? You have to first of all read the whole matrix. You will first of all read the whole matrix to convert it into a single 1D array. How much time it will take you to read the whole matrix? It will take you m cross n time to read the whole matrix. And then you will be having an array converted of m cross n length. On this array, you can apply binary search. So that will be of complexity log of mn. So what is big O of mn plus log of mn? This is big O of mn. And also here you are wasting space also of order of mn. So in fact, this optimization didn't work well for us because it is taking even more time, right? Okay, cool. Now, there is an interesting observation that we can make. Now, an interesting part that you can observe here is that maybe without storing the elements of this matrix inside a separate array, right? What we can do is, okay, let's write it 1D array here. Okay. So we'll say optimization 4. Okay. Oh, sorry. This is optimization 3. 1 second. This is optimization 2. And this is optimization 3. Okay. So now what if we can apply binary search directly on the 2D array? What if we can apply binary search directly on the 2D array without bothering a lot about the fact that You have to first of all convert this whole 2D array into a 1D array. Without doing all of that, if we can somehow apply binary search directly on this array, won't that be great? So let's take this 2D array, and we are going to exploit the property that every single row is sorted and the last element of every row is less than first element of the next row. So we can say that our search space starts from this index and ends at this index. Can I say that? So if you talk about the search space, then this lies from 0 to m into n minus 1, right? 0 to m into n minus 1. This is what we are pointing as low. This is what we are pointing as high, right? And because this is the last index, right, we are mentioning it as m into n minus 1. Why? Because if you would have converted this whole 2D array into 1D array, if you would have converted this whole 2D array into 1D array, this one will come at index 0 and this 60 will come at index mn minus 1, right? Now you might be thinking, sir, okay, you are referring this value as index mn minus 1, but in a 2D array you always refer every cell with a row and a column, right? But here you are just referring these cells with a single value. How using a single value I can get a row and a column? Very easily. So if you carefully see, I am marking this as index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. How many rows are there? 3 rows. How many columns are there? 4 columns, right? So this is the indexing that I'm doing. And can I say that if I would have converted this 2D array into 1D array, this would have been the indexes of all of these elements? Can I say that? If I would have converted this 2D array into a 1D array, right, then these would have been the indexes of every single element. Can I say that? 0, 1, 2, 3, 4, 5 and so on. Now, using these indexes, you can even get which cell in the terms of row and column we are representing. For example, this is row number 0, 1, 2. This is column number 0, 1, 2, 3. So what you can do is, if you want to tell which row you are at, you can actually divide your this index value with the number of columns. Just take a look. For example, you have 6. If you do 6 by 4 floor value, you get what? So let's say, let's do it like this. 0, 1, 2, 3, right? And let's write it like this. Okay. So if you have a row and if you have a column, okay, let's try to observe. Okay. At any point of time, if you do index by n, so what is 6? Index is 6 and n is 4, right? What is 6 by 4 floor value? 1. Can I say you are at row number 1? Can I say this particular cell is present at row number 1? And if you do index remainder n, so if you say 6 by 4 remainder value, what is 6 by 4 remainder value? 2. Can I say that? So can I say this is in column number 2? This particular cell is column number 2. So for example, if I give index as 6, right? So what is the row this particular index is present at? 6 by 4, that is 1. And what is the column? 6 mod 4, that is 2. So can I say this is present in first row, second column, right? And what is n? N is the number of columns. N is the number of columns. Can I say that? Right? So that is an interesting part. That is an interesting part that you can actually see. And it's a simple observation. It's a simple observation that you can take a look at. For example, you are at 9. If you do 9 by 4, this is going to come as 2. You can see you are at row number 2. And if you do 9 mod 4, this is going to be 1. And can you see you are at column number 1. So this particular cell comes at second row, first column. So now very easily you can do binary search. So let's start. Initially low is equals to 0 and high is equals to 11. What is the value of mid? 11 plus 0 by 2, that is 5. So we are actually pointing here. Okay. So the moment you get mid is equals to 5, you need to calculate which cell we are representing. So I'll say 5 by 4, 5 mod 4. 5 by 4 is 1, 5 mod 4 is 1. So this is this particular cell. Okay. Is the value 11 less than the target or greater than the target? Target is 3. Target is 3. So 11 is greater than the target. So what we will do is we will bring high here. We will bring high here. Okay. So let's call it like this. High. Okay. And for the next iteration, low stays 0, high becomes 4. Now let's calculate the mid again. Mid is going to be 2. That is 2 by 4, 2 mod 4. 2 by 4 value is what? 0. 2 mod 4 is 2. So you can say 0 comma 2, right? And you can see this is the second index. This is value 5. Is 5 greater than the target? Yes, 5 is greater than the target. So now what you're going to do is you will say high comes here. So low is equals to 0, high is equals to 1, mid value is 0, 1 plus 0 by 2. So you'll see, is 1 less than the target? Yes, 1 is less than the target. So you need to go to the right. So technically you will say low is equals to 1, high is equals to 1. So mid also equals to 1. Can I say that? So now low and high both are here and this value is equal to the target. As simple as that. So in this way, you can actually calculate whether the target element is present or not. And what we have done in a summary, is that each cell I have mapped to the same index they would have got if I would have converted this whole 2D array into a 1D array. And using these indexes, I can get the row number and the column number where a particular cell is present using this particular formula, right? Using this particular formula, which can come simply by observation. And now what is the time complexity? You can see what was the search space. Search space was from 0 to mn minus 1. So total number of elements were mn. So the time complexity is order of log of mn. And space complexity is O of 1 because we are not taking any extra space altogether. How cool is that? So if you want to quickly code this solution, okay, I'll say let low is equals to 0, high is equals to m into n minus 1. We need to get the value of m and n. So let m is equals to matrix dot length and let n is equals to matrix of 0 dot length. What is matrix dot length? Matrix dot length will give you the number of rows. And then for each row, how do you get a particular row? You can do matrix of 0, matrix of 1, matrix of 2 to get a particular row. Then what is the length of that particular row array? Is the number of columns. Right? Once you have this, we'll say while. Once you have this, we will say while low is less than or equal to high. Okay. Once you have this, we'll say low is less than equal to high. Straightforward binary search. Right? We'll calculate the mid. We can calculate the mid element. So mid is equals to low plus math dot floor of high minus low by 2. This should be let. Okay. And now you can actually first of all compare, right, that which element we are looking at. So I will say let row is equals to math dot floor of mid by n. Let column is equals to mid mod n. Okay, and then we'll check if matrix of row and col is equal to the target, right, we are going to return true. Else if the current element of the matrix is less than the target, we'll say low is equals to mid plus 1, else high is equals to mid minus 1. Right? That's it. And at last, if you never return true from above, we are going to return false. That means if you never found the element in the above while loop and the whole search space got exhausted, then eventually the element is not even present. You can never actually found that. And that's it. If you run the code, you can see The two sample test cases are passing. If I submit, you can see the solution is getting submitted, right? How cool is that, right? And that's how you can actually solve this problem. What is the time complexity? You can see the time complexity is order of log of mn, and that's what was the expected complexity as well. And if you want to implement this same solution in Java, so one second. Let's name it as search 2D matrix. Okay. So if you want to implement the same solution in Java, you can see the return type of the function is Boolean. If you will select Java here, return type becomes Boolean. Okay. You take the array, you take the target, you calculate the number of rows and the number of columns, you set the search space, then you calculate the mid, you calculate the row. Here you do not need to do floor manually because Java's division operator already gives you a floor value. Then you check if the value is equal to the target. If not, then you accordingly modify the search space and return false. As simple as that. That's how you can implement the same solution in Java as well. So this is a new question coming from LeetCode, problem number 374. Guess number higher or lower. What the problem says is that we are playing a guess game. The game is as follows. I pick a number from 1 to n. Okay, so there's the player, like the other player is there, who is going to pick any number from 1 to n. And you have to get, like, we as the user have to guess which number the other person has picked. Each time your guess is wrong, I will tell you whether the number I picked is higher or lower than your guess. Okay, so for example, like the value of n is 100 and the other person picked 35. So let's say if I will guess 54, so the other person will tell me that the number that you have guessed is higher than the number that I have picked. Then let's say if I say 12, then the other person will say the number that you have guessed is lower than the number that I picked, and so on. So you can say you have a predefined API. API, as in for the time being, you can assume that it's a function which returns three possible results. So what you will do is you can pass a variable num to this function. If this function returns -1, that means that your guess is higher than the number. Like for example, the number picked was 35 and we guessed 54, then it will return us -1. If it gives us 1, then our guess is lower than the number, like for 12. And if it is 0, then our guess is equal to the number. You have to tell which number the other person picked. Right, this is an interesting question. Now if you carefully see, there is no array. There is no array in this particular question. There is no set of elements that have been already predefined for you, inside which you are doing a few algorithmic operations up ahead, right? Instead, you have just a value n. You just have a value n, right? So this is LeetCode 374, right? Yep. You just have a value n. Okay. And this is the given value. And what we can say is that the other person has chosen something from 1 to n. So can I say the final answer is going to be between 1 to n? Can I say that? The final answer always is going to be somewhere between 1 to n. Yes or no? Right? But interestingly, in this problem, there is no array that has been given to you or anything like that. But what we can definitely say for sure is that in the range 1 to n, we have to search for the number picked. We have to technically search for the number which has been picked, right? So can I say this is very similar to a searching problem, that you have to search for a number. But in this case, you do not have an array to search for. Instead, you have, let's say, a logical range. You can say this is kind of like a logical range. And this range is of what? Logical range of answer. This is the logical range of an answer. And This leads us to one more type of binary search based problems called as binary search on answer. Okay, binary search on answer. Now, what is binary search on answer? In binary search on answer, generally you do not have an array or you do not have a collection of elements to play with. Instead, the search space is defined by some particular range or some particular logical range of an answer. Can you see? Here 1 to n is our search space. If I define the search space, then can I say the search space is from 1 to n only, right? Because our answer is going to lie in the range 1 to n. One of the values between 1 to n can be the answer. So this is the search space inside which we have to find something. So that's our search space, right? Now, inside this search space, we have to search for an element. How do you search for an element? Any element that you guess like x, you can pass it to the guess function. If the guess function returns 0, that means you have guessed the element correctly. If it returns -1, then your guess is greater than the actual number. And if it is 1, then your guess is lesser than the actual number. So what can be the brute force approach for this particular question? What can be the brute force approach for this particular question? The brute force approach will be to go to each and every value, in the range 1 to n and check if we guessed the right number. So how you will implement it? You will do something like this. For I is equals to 1, I less than equal to n, I plus plus. You will check if guess of I is equals to 0, we return, what do you have to return? I guess the value, right? We return I. Okay, we return I. Something like this, right? So you can see we are going from value 1 to n in the range 1 to n and trying to guess the value I. And can you see we are doing something like a linear search? We are doing something like a linear search, right? We are doing something like a linear search. That's why I'm classifying this as brute force. And this approach will give you time limit exceeded. Why this approach will give you time limit exceeded? Because if you carefully see, the biggest value of n can be 2 raised to the power 31 minus 1. Okay. So let's see how much is 2 raised to the power 31. So 2 raised to the power 31 minus 1 is this value. Can you see this is approximately what? 3, then 3, 6, 3, 9. This is kind of like greater than 10 raised to the power 9 or somewhere around the range of 10 raised per 9, right? This is somewhere around the range of 10 raised per 9. And we just will get 1 second for each test case. That means we have to do it in approximately 10 raised to the power 8 instructions. But here you will go beyond 10 raised per 9 instructions. So this solution should ideally give you TLE if lead code has set up the test cases well. Okay. Now how can we optimize? Now you can see, if we ask the question that how to optimize. Okay. So what we can say is that, you can see this is a search space. 1, 2, 3, so on and so forth. N minus 2, n minus 1, n, right? This is your search space. If I divide my search space into two halves, this is the left half and this is the right half. And let's say this is the mid value. Okay. So if I divide the search space into two halves, right? Then this mid value we can choose as a guessing value, that whether the mid value is the same value which the other person guessed or not, picked or not. If not, then we will check, is the mid value greater than my answer or less than my answer? If the mid value is greater than the answer, then everything to the right of mid is also greater than the answer. So my answer will lie in the left. And if the mid value is less than the answer, then my everything to the left of mid is also less than the answer. So my answer will end up in the right. So what we can say is that we can define the search space as 1 to n, and we say while low is less than equal to high, you calculate mid as low plus high, high minus low by 2, and I check, is the guess of mid correct guess? How do you get the correct guess? If the guess function returns you a 0, that means mid was the answer. So what do? You return mid. That mid is the value that the other person guessed. Else if the guess of mid is -1. What was the meaning of -1? If you get a -1, that means your guess is higher than the number. That means the mid value is greater than the answer. If mid is greater than the answer, everything to the right of mid is also greater than the answer. So we will never find the answer here. We will always find the answer in the left. So you do high is equals to mid -1. Else you do low is equals to mid +1. That's it. That's how you can technically solve this question in one shot, right? And it will not take much of your time, right? So that is the, I would say, interesting part that is actually coming up here, right? And if you see now the time complexity of binary search is log of the search space, right? What is the search space size? N. Size of the search space is n. So time complexity is log n. Space complexity is O1, because you are not taking any extra space, right? And that's how you can actually solve this question. Now let's try to submit this question with linear search first and see whether LeetCode has prepared nice test cases or not. So what I'll do is I'll say for let I equals to 1, I less than equal to n, I plus plus. If guess of I is equals to 0, you return I. See, that's it. If I run the test case, so smaller test cases are working. But if I will try to submit it, ideally it should give us a TLE. You can see time limit exceeded. So LeetCode has nice set of test cases. So what you can do is you can optimize it using binary search. So I'll remove all of this. I'll say let low is equals to 1, let high is equals to n, while low is less than equal to high, let mid is equals to low plus math dot floor of high minus low by 2, and if guess of mid is equals to 0, you return mid. Else if guess of mid is -1, you say high is equals to mid -1, else low is equals to mid +1, right? That's it. Let's try to run the code again, and let's try to submit it. You can see this time the solution got accepted, fair and square, right? So it's a pretty simple implementation, but gives us a good understanding and good intuition to how exactly binary search on answer actually works. So in case if you want to submit this same question in Java, this is how you are going to do it. Again, you are going to define your search space 1 and n, low as 1, high as n. You will keep on iterating till the time you exhaust the search space or not. You calculate mid, then you guess the value of the mid. If the value of the guess function returns you a 0, that means you found the element. If it is -1, that means your guess is greater. So you need to reduce the search space to the left side. Else you need to reduce the search space to the right side. If you will just take this function and submit it here, you can see this got submitted as well. So that's how you can actually code the solution in Java. So this is again a new question coming from lead code. This one, problem number 441, arranging coins. Okay, it's an easy marked problem. What the question says is that you have n coins and you want to build a staircase with these coins. Okay, so you have n coins and you want to correspondingly build a staircase out of it, kind of like this. Okay, the staircase consists of k rows where the ith row has exactly I coins. So you can see the first row has 1 coin, second row has 2 coins, and so on. And the last row of the staircase may be incomplete. You can see the last row here is incomplete, otherwise it would have got 3 coins. You are given a value n where n represents the number of coins. Return the number of complete rows of the staircase you can build. Okay, so what you have been given is, this is lead code 441, and the value of n is as big as 10 raised per 9. Okay, okay, cool. The value of n is as big as 10 raised per 9. Okay, what they are suggesting is that you have n coins. N represents number of coins. Okay, now you have to build staircase such that any ith row of staircase has I coins. Okay, so you can say in the first row you have 1 coin, in the second row you have 2 coins, in the third row you have 3 coins, 4 coins, and so on. And the last row can be incomplete. What we have to return is, using these n coins, how many complete rows we can make. How many complete rows we can make. Okay, cool. Now, how a complete row will look like? And they are assuming that let's say you are going to have k rows. Okay, so how complete rows will look like? In complete rows, in the first row of a complete staircase, you have 1 coin. Okay, then in the second row you have 2 coins, then in the third row you have 3 coins, fourth row you have 4 coins, fifth row you have 5 coins, and so on. In some k minus 1th row you have k minus 1 coins, and in any kth row you have k coins. Can I say that? Right, you can say first row has 1 coin, second row has 2 coins, third row has 3 coins, and so on. Right, okay. Now what is the total number of coins if, let's say, you make k rows? So let's say kth row has k complete coins. Okay, so if you have k rows, how many total coins you will need? How many total coins you will need? Can I say you will need 1 plus 2 plus 3 plus 4 plus 5 plus so on and so forth, plus k minus 1 plus k? Can I say that? If you want to build k complete rows, if you want to make k complete rows, you need at least these many number of coins. Can I say, to make k complete rows, we need at least these coins? Can I say that? We need at least these coins. And what is the value? You can see this is the sum of first k natural numbers. This is sum of first k natural numbers. And what is the sum of first k natural numbers? K into k plus 1 by 2. Right? This is the formula for sum of the first k natural numbers. So you can say that this is the number of coins that we need at least to make k complete rows. Okay, so k plus 1 by 2 at least coins we need
to make k complete rows. Okay. And how many coins do we have? How many coins do we have? The total given coins is n. So can I say the value of this k into k plus 1 by 2 should be either equal to n or less than n? Can I say that? That is, if you have to make k complete rows with n coins, then either this value should be equal to n or this value should be less than n. This value should not be more than n. Can I say that? Because if that value is more than n, then you do not have enough coins to make k into k plus 1 by 2 rows. For example, let's see a test case. For n is equals to 5, the answer is 2. Let's see why. For n is equals to 5. Let's say if you take a value of k as 1, this is what? 1 into 1 plus 1 by 2, that is 1, which is less than 5. If you take k as 2, then 2 into 2 plus 1 by 2, that is 3, which is less than 5. But if you take k as 3, 3 into 3 plus 1 by 2, that is 6, which is greater than 5. Can I say that? Can I say that? Can you see? K is equals to 2 is the largest value for which k plus 1 by 2 was less than equal to n. Can I say that? K is equals to 2 was the largest value. That is, this is the maximum number of rows. This is the maximum number of rows for which we have enough number of coins to create the complete set of rows. We need how many coins? 3 coins. We have 5 coins. So this is the number of rows that we can create completely. We cannot create 3 rows because we do not have enough coins for 3 rows, because 3 rows requires 6 coins at least, and we only have 5. Right? Let's take one more example. Let's say n is equals to 8. Let's say n is equals to 8. Now for n is equals to 8, if the value of k was 1, 1 into 1 plus 1 by 2 is 1, which is less than equal to 8. So one row we can completely make, no problem. If k is equals to 2, 2 into 2 plus 1 by 2, that is 3. It is less than equal to 8. So we can say we can very easily make 2 rows also. If you have to make 3 rows, 1, 2, 3, 3 rows. 3, 3 plus 1 by 2, that is 6. You can see we can even make 3 rows very easily using 8 coins. How? C, 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 C. You can see we use 6 coins here, right? So we can very easily make 3 rows completely. Can we make 4 complete rows? 4 plus 1 by 2. This is 10, which is greater than 8. So you can see we do not have enough coins to make 4 rows, because the number of coins required to make 4 rows is 10, and we only have 8 coins. So the biggest number of rows that we can accommodate is 3. So the answer is 3. So what you have to do is you have to search for this particular value. You have to search for the ideal value of k, the biggest value of k. So technically, we need to search for biggest value of k such that k plus 1 by 2 is less than equal to n. As simple as that, right? We have to guess the biggest value of k such that k plus 1 by 2 is less than equal to n, right? Now what I can say is that the value of k will lie in the range 1 to n only, right? Between 1 to n only, one of the values will be equal to k. Can I say that? Between 1 to n only, one of the values will be equal to k. So I can make this as my search space, and you can see inside this search space, let's say I get a mid value. Okay, what is this mid value? This mid value will tell us, okay, can we make mid number of rows? Can we make mid number of rows? How can you check whether you can make mid number of rows or not? You can do mid plus 1 by 2, right? If this value is less than equal to n, then we can say yes, we can make mid number of rows. See, within the search space, this is low, this is high. You calculate the midpoint and you try to check that whether you can make mid number of rows or not. And how do you check whether you can make mid number of rows? By doing mid into mid plus 1 by 2, right? If this value is less than equal to n, then yes, you can make mid number of rows. And then we will say that this is a potential candidate. This is a potential candidate, right? Otherwise, if the value of mid plus 1 by 2 is greater than n, then we can say we cannot make mid rows. Can I say that? We cannot make mid number of rows, right? Okay. Now, interestingly, what you will realize is that if you can make mid number of rows, then definitely you can make less than mid number of rows. For example, if you have enough coins to make 5 rows, then definitely you have enough coins to make 4 rows, 3 rows, 2 rows, anything, right? So the left side is irrelevant for us. In case mid is a potential answer, we will always go to the right. Otherwise, if you cannot make mid number of rows, let's say you cannot make 10 rows, then definitely you cannot make 11 rows, you cannot make 12 rows, you cannot make 13 rows. That means anything to the greater of mid is irrelevant for us, right? So we can check. I'll say value is equals to mid plus 1 by 2. I'll check. If the value is less than or equal to n, then I can say value is a potential answer. I will store it in an answer variable, right? Potential answer. And if mid is a potential answer, we can find a better value to the right. Why we can find a better value to the right? Because we have to find the biggest value of k that is less than that, such that k plus 1 by 2 is less than equal to n. If we found mid is a potential candidate, we can maybe find something better than mid, bigger than mid, because we have to find the biggest value of k. So if you want to find bigger value, you will move to the right. How do you move to the right? You say low is equals to mid plus 1. Else, in case value is less than n, then I'll say high is equals to mid minus 1. Why? Because if the value is less than n, you cannot make mid number of rows. So there is no point of considering higher than mid number of rows. You need to consider lower number of rows. And that's it. Technically, that is it. That is what we can actually do, right? And now you are applying binary search on a search space of 1 to n. So what is the time complexity? Time complexity is order of log of n. As simple as that. So if you want to code this solution, let's see. So we'll say that what is the minimum number of rows maybe you can make, right? See, the minimum value of n is 1. So at least you will be able to make one row, right? So I'll say let low is equals to 1 and let high is equals to n. I'll say while low is less than equal to high, let mid is equals to low plus math dot floor of high minus low by 2, right? Okay. And then I'll keep an answer variable. Minimum value of answer will be 1, so I'm keeping answer as 1. Okay. I'll say that let value is equals to mid into mid plus 1 by 2. Mid into mid plus 1 by 2. Okay. So I'll make it as math dot floor. Math dot floor of mid into mid plus 1 by 2. If this value is less than or equal to n, then we found a potential answer and we want to find a bigger answer. Otherwise, we didn't find any answer, we need to reduce it. At last, you can return answer. Okay, cool. Now, interestingly, you can think about a case where, let's say, if the value becomes exactly equals to n. If the value becomes exactly equals to n, let's see if our code already handles that case or not. Okay, so I'm for the timing commenting it out. If I run the code, you can see this looks accepted. If I submit the code, you can see it got submitted. So technically you can see we do not have to separately keep a check of value double equal to n. Why? Because we already have a check here that if the value is less than or equal to n, so when it will be equal to n, then also I will store the mid in the answer, right? And later return the mid. So you do not have you do not need to have a separate corresponding check for actually getting the value altogether. So that's why I always say that try to analyze the problem and then you will realize that there can be multiple ways to always solve one particular question. So I hope the overall logic behind the problem is clear to everyone. And let's say if you want to implement this solution in Java. So this is new file. Okay, so this is the Java solution. Again, you can see fairly straightforward and simple. You have to first of all separately prepare your search space. You'll prepare your answer. You calculate the midpoint. You calculate mid into mid plus 1 by 2. If the value is less than equal to n, that means you will be able to make at least mid number of rows. Mid number of rows. So now you want to find something bigger than mid. Otherwise, you always find something smaller than mid. As simple as that, right? So you can just submit this Java solution also directly. One interesting thing to analyze in this particular question, that again, we were not given any kind of an array inside which we had to search for a particular value. Instead, there was a range of an answer, that our answer was always going to lie between 1 to n, right? So there was again a range of an answer that we had to search our value from. So this problem also lies in the bracket of binary search on answer, right? Right. So in binary search on answer, you generally do not have a set collection of numbers. Instead, you might have to look at your problem and see that are you going to search for something maybe in a range of answer or something like that, and then try to analyze if the problem can be solved by binary search. How? That if you have a search space, can you divide the search space into two parts so that based on some property, one part is different, another part is different. Because here also you can see that, right? Based on this property of mid, that can you make mid number of rows, we can divide the two parts. If we can make mid number of rows, then we will always be able to make less than mid number of rows. So this part can be discarded. If you are not able to make mid number of rows, then we cannot make more than mid number of rows. So this part will be discarded. And again, we were able to apply binary search. So I hope the overall logic of the problem is clear to everyone. So this is a new question coming from lead code, problem number 367, valid perfect square. Quite similar to all of the problems that we have been doing as of now. You are given a number num, integer number value num. You have to return true if the number is a perfect square or false otherwise. What is a perfect square? A number is a perfect square, for example 16. The number which is a perfect square, it's the square of the square root is exactly equal to the number, right? So what kind of a number is a perfect square? A number is a perfect square if the square root value square is exactly equal to n, right? And square root values floor value. Okay, for example, if you take 16's square root floor value, it is 4, and 4 into 4 is 16. But you take 20 square root floor value of 20 square root is also 4, but 4 into 4 is not 20, so 20 is not a perfect square. So what you have to do is you have to check whether the given number is a perfect square or not. You cannot use the inbuilt square root function. Okay, now how can you do that? If you have to identify that whether a number x is a perfect square or not, if you have to identify whether the number x is a perfect square or not, you know that some number in the range 2 to x minus 1, some number in the range 2 to x minus 1 will be if squared and gives you x, then x will be a perfect square, right? So what I'm trying to say is, let's say x is equals to 16. Then what do you have to search is, if any number in the range 2 to 15, any number in this range, if you pick and you square that number, any number y that you pick and you square that number, if this square value becomes exactly equals to x, then x is a perfect square. For example, is 2 into 2 equals to x? No. Is 3 into 3 equals to x? No. Is 4 into 4 equals to x? Yes. So if you found a number whose square is equals to x, hence x is a perfect square, right? Now, you do not need to take 1 here, because you know that 1 into 1 is always 1. So it cannot make a perfect square for any other number. And you do not even need to take x, because the value of y for whose square is it should be equal to x should always be less than x, right? So that's why we are taking range from 2 to x minus 1. Now inside this range, you have to search for a number y whose square is equals to x. Now how can you search it? In the brute force approach, you can apply linear search, that you one by one go from 2, 3, 4, 5, 6, 7, 8, and so on. Or you apply something optimized. What can you do is, you can apply binary search. In binary search, you can say you will take a mid value between 2 to x minus 1. If mid into mid becomes exactly equals to x, then mid is your answer. If mid into mid is less than x, that means this value square is less than x. So everything less than mid square is also going to be less than x. So we should go to the right. How do you go to the right? You say low is equals to mid plus 1. Otherwise, if mid into mid is greater than x, then you should say high is equals to mid minus 1. Why? Because if let's say the square of mid is greater than x, then everything to the right of mid, if done square, will also be greater than x. So the actual value should always lie on the left side of the mid, right? Think about it like this. For example, x was is equals to 16. You went from 2 to 15. 15 plus 2, 17. By 2, the mid value is 8. Now what you will do is, you will see 8 into 8 is 64. Is 64 equal to 16? No. Is 64 less than 16? No. Is 64 greater than 16? Yes. If 8 into 8, 64 is greater than 16, then if you will square any value to the right of 8, that value will also be greater than 16, right? So that is never going to be your answer. And you will go towards the left side. And this is how, again, in order of log n time, you can still solve this question, right? So I'm not going to code this question for you, but I believe the coding implementation of this question should be more or less straightforward. Now there is a quick homework that I would like to give you. We talked about the brute force approach using linear search. What I want you guys to do is try to think what will be the time complexity of the brute force. What will be the time complexity of the brute force approach? A hint that I can give you is, it is not order of n. It is not going to be order of n, right? If you implement brute force in a slightly smart way, then the complexity is not going to be order of n. What is the time complexity? Try to think about it.